This session is Harry Gray from Caltech, and he's been working in solar photochemistry since 1966, which means he started before Mark, Jen, and I were born.
That's right.
So he knows a lot about the subject. He has won the National Medal of Science, the Priestley Medal, the Wolf Prize, and the Welch Award in Chemistry, amongst other things. And today he's going to talk about solar fuels.
Thanks very much. I like to work out in the audience. I'm a man of the people. I also know Dr. Seuss. I memorized a lot of Dr. Seuss books, like Sleep Book is one of my favorites. The news just came in from the county of Keck that a very small bug by the name of Van Vleck was yawning so wide you could look down his neck. And that goes on and on. I could give the whole thing, but I actually want to talk about solar fuels. This area has three fundamental parts, and you've heard a lot about the first one in the first two talks. I think those speakers covered light absorption very, very nicely, so I won't spend much more time on it. Just suffice to say that we have to efficiently absorb all the sunlight that reaches the Earth's surface, filtered by the ozone layer. Instead of degrading it to heat, we've got to do electron-hole separation, and this is very easy to do if you're willing to degrade the free energy. But if you're not willing to degrade the free energy and keep about 80% of the excitation energy so that you have enough energy to split water, which is what we want to do to make fuel, this is a very challenging proposition to get electrons and holes apart long enough with enough energy to in fact interface them with multi-electron systems that make and break chemical bonds, and these we call catalysts. And the development of catalyst is one of the big areas of my program, and I will talk more about that than I talk about these other two fundamentals, although I will mention them as I go along. It was pointed out I actually started in this area in the 60s, even when I was at Columbia. Before I got to Caltech. And I thought a lot about this problem, and 31 years ago, I laid out the territory for solar fuel formation in an article in Science with Andy Maverick. The territory if you wanted to use molecular materials, not solid state materials. And of course, I could still recommend that for reading, although I've had a number of very brilliant students along the way, two of them, Nate Lewis and Dan Nocera, of course, like to show me up as much as possible because they claim I'm probably over the hill. And so they wrote this very long paper in PNAS, which you may not have read, and if you haven't, I advise you to go to my article here. I usually come along after Nate and Dan Nocera and write a summary in one page of what they've just told you. And of course, I'm just kidding about this. I'm very proud of my former students. They've done spectacular work. I put this slide up just to give a shout out to John Turner's work at NREL, which really got us going in this particular program. John Turner at NREL showed us a strategy to make solar fuels involving layering two semiconductors, a lower band gap semiconductor, gallium arsenide, with a higher band gap, gallium indium phosphide, with a two-photon, two-electron strategy. It's very, very hard to split water with a single photon strategy for one hydrogen. It's better to get two photons. You get a red and a blue. You get two electrons out of the conduction band at the surface. You make hydrogen. Holes then come over to this big platinum electrode where water is oxidized to oxygen. This is a very, very nice demonstration. It gives us a strategy for how to use semiconductors in tandem to actually do multi-electron work. The only problem, and this talk would be over now were it not for one frightening fact, and that is we can't scale this wonderful device up. It's the world's record water splitter. It's over 12% efficient, sunlight to fuel. And we've been living off natural photosynthesis since the beginning of civilization, which is less than 1% efficient light to fuel. So why not? Well, if you cost this up, it's got a lot of platinum in it, and we can't afford to use platinum and scale up. We don't have enough of it. It's too costly. Nate actually costed this out, and he estimated it would cost $50,000 a square meter to scale this up. And of course, in order to scale up something, we're going to have to do something like $100 to $200 a square meter. So my program, which I started, Sally, with GSEP funding, startup funding from GSEP many years ago, has now been highly leveraged up to a huge program with the goal of building something as good as John Turner's device, but making it out of very cheap materials, earth-abundant materials, things like iron, cobalt, tungsten, nickel, copper, and so forth. I put together a small research group to attack this problem. This started with GSEP, Sally, and has grown into, if you want to talk about leveraging, this is a good example. Even got a guy at Stanford here, Tom Jaramillo, working with us, a wonderful guy here in our program. You can see all the principal investigators. We've got also lots of industrial partners, DuPont, Dow, 3M, and so on, BP. With the goal of really getting a scalable solar water splitter. Harry Atwater's folks gave the last two talks, and of course we also have drained Harry Atwater's brain like everyone else has in getting the proper aspect ratios of our micro-rod photo anodes and photocathodes, long dimension here with a short one here to get holes out to the surface and electrons out to this surface. This photoanode now is tungsten oxide microrods, and our photocathode is silicon microrods, 200 or 300 microns. We used to call them nanorods and realized they were bigger than nanorods, and now we call them microrods. A membrane separator, which conducts electrons and protons, and very importantly, catalysts on the tungsten oxide and catalysts on the silicon to convert the electrons at this surface and with protons into hydrogen, and the holes at the tungsten oxide surface with water into oxygen. Catalysts, as you will see, are absolutely crucial. So let's start with the catalyst. If we start thinking about what we should use as an earth-abundant material, we asked, of course, nature. Nature had to use earth-abundant materials, and the best catalysts for hydrogen evolution are hydrogenase enzymes, which have these complicated structures with active sites that are iron and sulfur and a few things like this. If we put these very highly efficient hydrogen producers on our silicon microrods, they don't last very long. They're too fragile. On excitation, they erode away, they oxidize away very quickly. They last only a few minutes. Then somebody will say, well, Harry, just take the active sites out and rebuild them as bioinorganic chemists do. Just use the active site on the surface. But I'm afraid to let you know now that after 30 years of work in a field called bioinorganic chemistry dedicated to making these kinds of synthetic analogs, we have learned one important lesson. When you take the active sites out of the protein, they don't work anymore. they need the interactions, the weak interactions, the multiple non-covalent interactions, the hydrogen bonds, the hydrophobic contacts, the folded protein medium in order to tune their redox potentials into the sweet spots. When you bring them out, they're about 1 volt off in potential, and they're 1 volt off the wrong way. So the bottom line is we can't use these as catalysts on silicon microrods. We don't have enough potential to get out to use them. So our program has been making synthetic catalysts, molecular catalysts, and the rest of the world has too. I don't have time to give you the rest of the world talk because Sally didn't give me enough time in this talk to tell you the rest of the world. So I'll just give you the Caltech Hall of Fame. We have developed 5 very active, low overpotential hydrogen evolving catalysts with these students and postdocs, some of them undergraduates at Caltech. 4 of them have cobalt in them. 1 has iron. We have made the first actual good iron molecular catalyst out of this highly fluorinated ligand here to tune the potential right. But I will, in this talk, just talk briefly about these 2 cobalt catalysts where we actually have worked out the reaction mechanism. There's a feeling in chemistry, if you work out the mechanisms of reactions, you can actually learn enough to go back and synthesize even better catalysts. Occasionally that's true. In our case, it has been true. We have worked out these mechanisms in detail for these 2 systems. It starts with electrochemistry, getting electrocatalytic waves out of hydrogen evolving reactions where the Faraday coefficients are essentially perfect. And you get hydrogen evolution with these catalytic waves, electrocatalytic waves, which you can simulate with mechanistic models in which you estimate rate constants and mechanisms. And this was done in the first go-round of this work, leading to 2 mechanistic proposals. 1, the French mechanism, and the second, the American mechanism. Of course, they're different, as you might expect. With the same data, the French group said that at an electrode, cobalt-2 is reduced to cobalt-1. It picks up a proton to make a cobalt-3 hydride, and that's protonated directly at the electrode to go back to cobalt-3 and hydrogen coming out and coming then back in the system this way. The American group, with the same data, simulated it and said, no, that doesn't work. You've got to get 2 cobalt-3 hydrides to collide together in a bimolecular mechanism to split off hydrogen in a homolytic pathway in red here that comes around and then comes back to cobalt-2 and back in the system. This is the American one, the French one. And then a couple of theoreticians got in the act. You know, this is the bane of all experimental work. Theoreticians always stick their nose in your business and tell you what you should be doing. And that happened in this case. The 2 theoreticians came, they would be nameless in this talk, and said, Harry, both the American mechanism and the French mechanism, they're both wrong. What you need to do is put another electron into the cobalt-3 hydride, and they suggested the potentials of that would be reasonable to make a very active cobalt-2 hydride. And after I got over my initial dislike and my initial problems with the theoreticians, I went back and said, well, okay, let's do some experiments to check this new mechanism. In order to do that, you have to generate this cobalt-3 hydride very, very quickly. And that requires a fancy laser experiment. It involves starting with something we call a photoacid, bromonaphthol, which when excite with a laser, do intersystem crossing to its triplet. Its triplet state is a very powerful acid. It lives long enough to protonate after the laser pulse, protonate in the diffusion limit to cobalt-1. to make the cobalt-3 hydride very, very quickly. And then, sure enough, the excess cobalt in solution reduced, and we can follow this directly with transient absorption to the cobalt-3 hydride, to the cobalt-2 hydride, and sure enough, that makes hydrogen, and we can watch all 3 steps and resolve them all. Call up the theoreticians, apologize to them, thank them for their information. Their mechanism seems to be right. That, in fact, you do have to add 1 more electron to the catalyst to make it work. But I wanted to make sure of that, so I wanted to slow this down so I could literally see the cobalt hydride and watch it go to this. In order to do that, I had to slow the reaction down. So we built this tripodal phosphine system, which evolves hydrogen slowly. We have all the structures slowly enough that by NMR, we can watch the cobalt-3 hydride come into as an intermediate, and we can watch it literally reduce to the cobalt-2 hydride by NMR. There's the textbook spectrum of the cobalt-3 hydride, the textbook second order in cobalt kinetics that we see. And it's inverse order in acid, which means there can only be 1 mechanism that really works, and that is the one the theoreticians predicted, namely this one. We required the cobalt-3 hydride. In order to activate it, we have to get a cobalt-2 hydride, and that is extremely active intermediate for hydrogen evolution. So what did we learn? We learned we've got to now build new catalysts with redox active ligands with potentials that are tuned right into the sweet spot, so we have an electron parked. Just when we make the intermediate hydride, we can pop an electron, another electron, right in. And we made that complex. We made it. It's a bisaminopyridine. It's an extremely active hydrogen evolving catalyst made by these interesting ideas that were initially figured out by theoreticians, and we followed up with experiments. We have some now extremely active hydrogen evolving catalysts that are robust and working in aqueous solution. So now we're putting them on silicon microrods by covalent attachments through vinyl linkages and so forth. We have a lot of activity by then coupling these catalysts to silicon. We also have a lot of activity of putting heterogeneous catalysts on silicon, and this is our best example, electrodepositing nickel molybdenum alloy directly on silicon to give a integrated photocathode that's just as good as platinum on silicon. And so we've published this. These are all the references. So we now have hydrogen evolving systems on our silicon photocathodes that are just as good as platinum systems, and they're cheap, and they're quite efficient. So we've got to do water oxidation. Who's keeping up with the time? Sally, are you keeping up with the time? You're the boss. How much time do I have, Mike?
10 minutes.
I have 10 minutes? 5 to 10. 5 to 10. Don't tell me that. Okay, just keep me on time, okay? We now got to do water oxidation because we don't want to get the electrons on the cheap. We've been doing that since the beginning of civilization. We get them on the cheap from oil, gas, and coal. We need hydrogen just directly just to make ammonia, an ammonia plant. Talk about all the hydrogen that's being used now. We desperately need to make it from water. Well, and our tungsten oxide photoanodes, we have them, and people have claimed if you irradiate them, the band gap's large, the valence band is deep, so it thermodynamically can easily oxidize water, but it doesn't in the presence of sulfuric acid or hydrochloric acid. There's the valence band. It's very deep, so you get a hole down here. You can do all these reactions, but what you really do without catalysts is you oxidize the anions of the acid. You oxidize sulfate to the sulfate radical, which couples to give you peroxydisulfate. With HCl, with hydrochloric acid, you get chlorine instead of oxygen. So you need catalysts on the surface, And Kwang-Chen in our group, who was at Purdue and has now moved to Wisconsin, put Dan Nocero's cobalt oxide catalyst on tungsten oxide to build an integrated system that actually does work pretty nicely. And this is a tungsten oxide photoanode decorated with a cobalt oxide catalyst for water oxidation, and it does water oxidation with nice paradigms. So we have these devices. They're not as efficient as we would like, so we would like to improve them. One problem is tungsten oxide band gap's too high. It's 2.5 electron volts. We want to move it down to the sweet spot's about 1.7. And so we need better photoanodes. We need to tune this somehow, and now we figured out how to do it. If we synthesize tungsten oxide, starting with ammonium tungstate in a highly oxidizing environment, we can convert the ammonium into dinitrogen, molecular nitrogen, which inserts into the tungsten oxide lattice, expands it beautifully, and changes tungsten oxide from a band gap of 2.5 to a nitrogen-doped, molecular nitrogen-doped tungsten oxide, which is red with a band gap of 1.7. And there it is. This paper's in press. It's about to be published. There's the signature, the vibrational signature of just molecular nitrogen, N14 and N15, which we stick in the middle of tungsten oxide. It's stuck in there. Our synthetic method sticks it in there, and it doesn't come out until you heat it up to 600 degrees. And it turns it red and makes it into a beautiful photoanode, operating even out to 550 nanometers now, making oxygen with catalyst on the surface. So we now have a very superior photoanode. So finally, now do I have 3 minutes left? Mike? Okay, good. So now we need even better catalysts. And the last talk told you what we need. We need small nanoparticles. The smaller, the better. You heard from the last talk, you get down to very, very small nanoparticles, you get great catalysts. And so we've got a program to make really small nanoparticles, quantum confined systems that we believe will be absolutely superior catalysts, both for water oxidation and for water reduction. And we're doing this by pulse laser ablation. We're tuning a high-powered laser, a triple YAG, right down the pipe, right down at materials that we have confined in water, and we're heating them up with this high-powered laser pulse, usually about, well, we go from 30 millijoules per pulse up to 150 or so, but 30 millijoules is good. We create a plasma down in the water, the plasma at 5,000 Kelvin at high pressure, and then cools into very small nanoparticles, very uniform, very nice synthetic method. There they are. This is the cobalt oxide one, so we hope to make all kinds of nanoparticles this way, about 3 nanometers. And they're quantum confined. You know, cobalt oxide is black, but our 3 nanometer cobalt oxide nanoparticles are yellow. They're yellow, quantum confined. I got some interesting ideas from the last talk about how maybe to probe their activity. So this has been a nice session, at least from my point of view. And they're terrific catalysts. They're terrific catalysts. Normal bulk cobalt oxide is an electrocatalyst. It has no photoactivity. It's black. These things are yellow, and they have very nice blue light photoactivity with pulses of oxygen. As we pulse this for 30 seconds, we get a pulse of oxygen out. These are terrific water oxidation catalysts, small nanoparticles made by pulse laser ablation. So we're going to expand this program, and we're ready now to put these on our photoanodes, hopefully to make even better integrated systems. This is what some of our stuff looks like. We can make it into rugs and so on. This is a report. I've given you a report from our group. I think I've gotten under the time limit? I hope so. The two stars of this talk are these two brilliant young women, Smiranda Marinescu and Jillian Dempsey. Jillian just left my group. She's now assistant professor at North Carolina, Chapel Hill. Smiranda is still in my group now. A shout out to GSAP here, Sally, who really started this whole activity of ours, which is now expanded into this very, very large NSF-supported program with many investigators all over the world, and I should say hundreds of students. I call them my solar army. I've got hundreds of students searching for new materials, posting hits on the web with activity kits that we have, and we're now taking some of those hits that we're getting off the web by kids in high schools, colleges, all across the world, who are posting them in with new materials that they're discovering with activity that we're now planning to formulate into these small, very, very active nanoparticle catalysts. We have an annual retreat every year. I rent a hotel in Huntington Beach, invite all these kids and all the principal investigators. You'll see some of the usual suspects up here. Nocera's somewhere, Nate's up there somewhere, Sally. Probably hiding, I don't know. Anyway, the kids then go way back into here. There's a bar back here. A lot of my kids are back here. Anyway, thank you very much for your attention. I see Art. He's all over me now. Yeah.
I don't know enough about chemistry. Why do you go to cobalt?
You know everything about chemistry. Don't give me that line.
I'm not a chemist.
I know you're not, but you know a lot of chemistry.
No, but anyway, why did you pick cobalt?
Why did we pick cobalt? Because in ligand field theory, if you want to make a semi-stable hydride, you want to make a D6 low-spin configuration, pseudo-octahedral geometry, and cobalt-3 is where you want to go for that, for the hydrides that are just stable enough so that you can go from there. And if you want to, and so there's electronic structural reasons to go to a D6 low-spin configuration for your intermediate hydride. So it's you can make it from protons. You can protonate a cobalt-1 to go to a cobalt-3. If you went to the same argument, and the reason iron is such a problem, you have to go to iron 0 up to iron 2, and the iron 0 with ligands is very, very hard to get to in potentials. They're much too negative. I shifted them back with fluorinated the system, but the answer is it's electronic structural reasons. It's stability of certain electronic structures and certain geometries. It's all those considerations that suggest that if you want a homogeneous catalyst through hydride intermediates, cobalt is the best place to go. Iron then requires a lot more thought about how you're going to tune the potentials down to work through the same kinds of cycles, but we're working on that now. And what our work has added into it, this idea of adding redox active ligands that you can put electrons in at low potentials. If you add that to the mix now, you can expand the base from cobalt to iron to other metals. But the answer is electronic structural reasons, stability of hydrides, not too stable. If they're too stable, they won't go anywhere. They have to be just right so that you can protonate them off in some form or another. And what we learned from the theoreticians is we have to add one more electron than even we thought in order to get really great activity.
And when you finally get the hydrogen, how do you get it out?
It bubbles out.
Bubbles.
It bubbles right out. Yeah, you get tremendous bubbling out. Yeah, in fact, these are really nice systems to make demonstrations and so on. It's easy to get the hydrogen.
What is the overall efficiency?
It depends on which system, but if we take our best, say our system with silicon, with certain wavelengths and so forth with a nickel molybdenum catalyst, about 7%. And right now, we think we can build a whole integrated system. We've got all the components now, actually, put together in various pieces. We think we can build a demonstrator now that overall will be around 2% efficient overall. The hydrogen part's about 7% right now. Of the best systems, of course, we've got a lot of systems, and the best ones we have are in that ballpark. So we've got a ways to go, but we're getting there.
Okay, we have time for one more question. No, if there are no more questions, let's thank Barry again.
Thank you.